Hi everyone, this is my first attempt at a screen capture video lesson. I'm going to try to keep it as short as possible, but I thought it might be nice just to hear my voice and see me work through some questions rather than trying to figure it out on your own. So this is a lesson I chose to try this out on, this hypergeometric lesson. I'll also be touching on some concepts from the first couple lessons and probability distributions in general. So this is the last lesson that we're going to do in this unit, so it's pretty short. So we'll be expecting another assignment coming up probably by the end of the week. Please, please, please do not leave that to the last minute. I'll post a review. I'll give you a few days to get ready, and I'll give you a few days to work on the assignment as well. Okay, so a probability distribution, as opposed to the last unit, which was just probability, is just a table or a graph that shows the probability of all of the outcomes and not just a specific outcome. So all those concepts you learn in probability has the potential to carry over in this unit as well. What we found in the last lesson with the binomial distribution was sometimes there's a unique set of circumstances which fit in to a specific kind of distribution. The one was binomial, this is hypergeometric. They're very similar except for one key difference, and we'll go over it right now. Now the good news is if you read this first question with this investigation, you can do this question right now. I could have asked this question on your last assignment and you could have answered it using combinations. Suppose there's a bag of 15 marbles, 9 white, 6 black. If you pull out 4 in a row, what is the probability that you would pull out exactly 2 black marbles? You could do this using combinations. What you didn't know was that this is actually a hypergeometric distribution. I'll explain why. So first we'll look at why is this not a binomial distribution like we saw in the last lesson. So are there exactly 2 outcomes when you pull out a marble? Yes, there is. It's either going to be black or white. Did they specify the number of trials? They did. You are pulling out 4 marbles. A success would be pulling out a black marble, and a failure would be pulling out a white marble. Now, is each trial independent? Because for a binomial distribution, each trial had to be independent, meaning those probabilities did not change. That's why you were able to define P for a probability of success and Q, the probability of a failure. So are these trials independent? And if you read the question carefully, it says without replacement, which means you're not putting the marble back in the bag. So that means if you pick a white marble first, we know the probability would be 9 out of 15. Well, the probability of picking a white marble on your second draw is not the same. It's no longer 9 out of 15 because you're not putting it back in. So it's going to be 8 out of 14. That's what makes these trials dependent, not independent. Okay, so if they fit, so it fits the exact same criteria as a binomial distribution, except the trials are dependent instead of independent. So that example above is a hypergeometric distribution. So I'm going to post this note as I would normally. I'm not going to go through all the examples. I will go back and fill them in, so it will be a completed note that will be posted. I'm just going to try to just keep this reasonable length. I'm only going to work through a couple of the examples. Okay, so this is what I just stated. The only difference with hypergeometric is the trials are not dependent. Each trial is dependent. So are there 2 outcomes? Yes. You're either going to have a success or failure. Okay, there's no in between. Whatever you're talking about, it's either going to happen or it's not going to happen. You're either going to pick a man or you're not going to pick a man. You're either going to pick a white marble or you're not going to pick a white marble. Are the trials specified? It has to be specified. And again, the main difference here is the trials are dependent. instead of independent. Alright, so the random variable x then, as for any probability distribution, will be the number of successes. And there we have it. Okay, so let's move on to this example. So this is the example that was put out in the intro here, exact same one, except it's asking for the probability distribution. So anytime a question's asking for a probability distribution, it wants the probabilities of all the outcomes. So it's a bit of a tedious process, but it is what it is. That's what it wants to see. So you can do this by a table or a graph. We're going to do both. So probability distribution for selecting black marbles. So what I'm going to do is I'll define my random variable. Let the random variable x represent, I could say the number of successes, but specific to this example, it'll be the number, I'll write that, number of successes, in this case, the number of black marbles picked. Okay, and therefore our range of x, well, if I'm picking 4 marbles, what are the possibilities for the number of black ones I could have? I could have 0, 1, 2, 3, or if I'm very lucky, I'm going to get all 4 of those being black. So what this question's asking for, or any question that's asking for the probability distribution, it wants you to show the probability of all of these outcomes in the range. So that's what I'm going to do. I'm going to quickly set up a table here. Okay. So I'll probably need to use a couple columns here. So you'll set up x, and then you'll have your probability of x. And again, the good news is we already know how to calculate these probabilities. So my first possibility, what's the probability that I pick out 0 black marbles? Well, there are 6 black and 9 white, so the number of ways I pick 0 black marbles are 6 choose 0, which means they're all white. So the number of ways I pick that they're all white is 9 choose 4. Over the total number of possibilities, well, there's 15 marbles total. It's going to be 15 choose 4. So I've already taken the liberty of doing these calculations. So if I look down here, it should be 126 over 1365. Okay, that is the probability you'll pick 0 black marbles, approximately 9%. So what I have to do now is do this for all the possible outcomes. So again, it can get pretty tedious. So now I want to know what's the probability of picking exactly 1 black marble. Well, I have 6 black marbles. How many ways can I pick exactly 1? 6 choose 1. That means I'm going to be picking exactly 3 the black marbles. It's going to be 9 choose 3 over 15 choose 4. And again, I've already taken the liberty of calculating this for you. 504 divided by 1365. If I was really savvy at this, I'd be able to fast forward this part, but we're just gonna It's my first time doing this, so we'll just have to work through this. Luckily, we're only picking 4 black marbles, though. So, probability picking exactly 2 black marbles. Well, there's 6 black, so 6 choose 2. That means I'm going to be picking exactly 2 white. Alright, so that should be 540 over 1365. Alright, so as expected, I ran out of room here, so I'm going to continue with the last 2 possibilities over here. So the probability of picking exactly 3 marbles, get that out of the way. Well, there's 6 black, I'm going to choose exactly 3. Which means I'm picking 1 white, out of 15 choose 4, and I get approximately 13%, or 180, I think is what I have written there, over 1365. Very rarely will you be asked to do the whole probability distribution. You can imagine if I asked something like this on a test, this is very time consuming, so you might just be asked to do part of a probability distribution. But we got lots of time right now, so we'll go through the whole thing. So here we go. What is the probability that you get really lucky and you pull out all 4 black marbles? Sorry for that watermark. I downloaded this. I can only get the basic version of Smart Notebook here, so I got to deal with that. It's 15 over 1365. Okay, so this question is over, which is approximately 1%. So when you're asked for a probability distribution, this is exactly what they want. Question's over. Here's all my possibilities, my number of successes, and here's all the probabilities that go with them. Okay, so you would have seen in the last couple lessons some questions asking you for what's called expected value. So what this is they kind of want to know, on average, specific to this question, how many black marbles would you expect to pick? So if I ran this experiment an infinite amount of times and then averaged out my results, on average, how many black marbles would I expect? And just looking at the question, you see that there's less black marbles than white marbles. So if you're picking 4 times, you wouldn't expect 2 black and 2 white on average. You're probably going to expect, on average, less than 2. Because you're more likely to pick out a white marble because there's more of them. So the way you calculate expected value manually, if it's not a binomial distribution or a hypergeometric distribution, is you have to do this. You have to go through this process. So what I'm going to do is calculate the value of the random variable times its probability, and then add them up. Make sure that line is blue. Okay, so you would have seen in the previous lessons this third column that I was adding, and I would label it X times P at X. So this is me taking the value of the random variable and multiplying it by its probability, and then adding all those up. And the number at the end, it has no units assigned, that is the expected value. So 0 times this would be 0. 1 times 504 over 1365 is going to be 504 over 1365. 2 times 540, so I'm just multiplying fractions here, so top times top, bottom times bottom. It's 1080 over 1365. 3 times 180 is 540. And finally, 60. 4 times 15 is 60 over 1365. Now what you notice is in the first two lessons of this unit, this is the process you had to do. It wasn't a specific kind of distribution, so this is what you had to do. You had to show all the outcomes, you had to calculate all the probabilities, and you had to multiply those outcomes by the probabilities and add them up. When we did a binomial distribution, you didn't have to do all this. If you could classify it as binomial, there was a formula that would get you directly to the expected value. It was n times p. So that's very useful to save you the trouble of doing all these calculations. Alright, so what is my expected value? Denoted e to the x. How many black marbles would I expect to pick out on average? So this plus this plus this. I'm just adding up all these green values. They all have the same denominator, so that's why I'm able to add up all those numerators and divide it by 1365. And then that would equal, I believe, 2184 over 1365, which equals 1.6. So if you're ever asked to interpret what this means, that means that on average, if you were to do this experiment, you would expect to pick out 1.6 black marbles. Of course, you can't pick out 1.6 black marbles as an actual result, but it's an average. Alright, so lastly, they want us to show this graphically. You know what, I'm going to try to save some time by not doing this fully, but if you can check back to in the completed notes section, you'll see a nice completed graph. But basically what this is this is a graph that's showing all the values of the random variable at the bottom. You'll have a nice little title, and then you'll have all the probabilities. So the highest probability we have looks to be about 40%, so I'd probably go up by 10% on the side here. No, I'm almost done the whole thing. I might as well keep her going. Okay, we'll call this marble game. Sounds good. Keep it simple. And then I'll get the line here, make it a little thicker, make it blue. Alright, so the probability that we are going to pick out 0 marbles, I've already gone ahead and calculated. I know these results as decimals, I didn't write them out. But this one, if you divide it, it equals 9%. So you would put a little line like this, up to about 9%. The next one here, one black marble, this probability equals 37%. So that'd be about here. And then 2 black marbles, which is the most probable outcome, is very close to 40%. And then they're doing it. Then 3 black marbles would be 13%. And then lastly, this is about 1%. So very unlikely you're gonna get all 4 black marbles. Oops. Did not get my line there. Try that again. No, just won't do it. Alright, draw a little line here, then I'll bring it over. You know what? We'll just forget that. We'll go here. Make this nice and thick. So usually they put a little circle on the top of these. So because this one's 1%, you won't even see the line. So there you go. There you have it. So that's what they want when they want the probability distribution graph. Now, lucky for us, like a binomial distribution, there is a formula that you can use if you want to calculate the probabilities of a hypergeometric distribution. What I'm telling you right now is that we don't need, did we use this? No, we did not, because we already had the skills. We already had the skills from the last unit. But if you were to put in, these values of A, N, R, X, you would get these exact values. Time permitting, I can show you that, but what I would encourage you to do is if you are able to identify this as hypergeometric, that's great. Just go ahead and solve it, just like we did here. I did not need the formula to calculate these. But if you like formulas, you're a big formula person, then feel free to use this formula. I will go over it at least one time for you. What is useful though, and I can't stress this enough, is this. There's a direct formula for the expected value. So if a question just asked you for the expected value, you would not need to go through this if you're able to identify the values of R, A, and N. So what are these values of R, A, and N that they speak of? Well, A is the number of successful outcomes in the population. So I'm going to apply this to the last example. How many successful outcomes did we have when in the marble game? Well, that would be the number of black marbles. So in this case, that is the number of successful outcomes. The successful outcome is picking a black marble. There is no X variable, we don't need to worry about that. N is the total number of possible outcomes. Well, how many possible outcomes were there? There were 15. And then R is the number of trials we did, the number of dependent trials. Well, how many times did we pick these marbles? 4 times. So if I were to put these values into here, look what I get. E to the x equals R times A over N. So that's 24 over 15, which equals the 1.6, which is the same value you get from doing all this work and then adding them up. So you'll definitely want to be using this formula if you're able to identify it as hypergeometric. You don't need to use this formula. I may or may not show it to you one time. You can look in the textbook. It would run through that example as well. Most people choose not to use this. Alright, so I think I'll go through maybe one more example here. So this is very similar to the last example. Maybe I'll just set it up. Ignore that. Determine the probability distribution for the number of women on a civil court jury. So there's 6 members from a pool of 8 men and 8 women. So the random variable x would be the number of successes. The number of the range, the possible outcomes would be 0 women, 1, 2, 3, 4, 5, and 6. So it's a pretty big chart. So if I were to just do one of these, just say I were to do if I were to set up the chart, like this, I could have 0 women, I could have 1, I could have 2. Okay, so if I were using the formula and I want to know the probability of exactly 2 women, well, I would have to do this. A is the number of successful outcomes. So how many successful outcomes do I have here? In other words, how many women are there? 8 men, 10 women. So there's 10. Okay. N is the total number of trials. Or sorry, the possible outcomes. So there's 18 people. The number of trials R is, we are picking 6 people. And then X is going to take on the different values that I'm solving for in that moment. So if I wanted to do 2, for example, I would put in this. And to use the formula, I would go A, choose X. So 10, choose 2. Okay, and that's how you pick exactly 2 women. And then it wants me to do n minus A. Well, what's n minus A? That's going to be the number of men. Total number of people minus the number of women. And then how many men am I picking? Well, that's going to be the number of trials minus the number of women that I'm picking. So it's going to be 6 minus 2. So you're going to end up with 8, choose 4. Which is basically the same as the number of men that you're choosing, and we're choosing 4. And then over here you get n, choose R, so total number of outcomes. So that would be the 18 total, and I'm choosing 6. So again, very quickly, 10, choose 2, you get 8, choose 4, over 18, choose 6. So that's using the formula, but look what it gets you. That's exactly how I would have calculated this had I not used the formula. Alright, so I'll erase this, complete it properly, and it'll be in the posted solutions. If I go to the next page, it wants the graph. You can do that on your own. The expected number of men on the jury. So I don't have to do the whole distribution because I have this, RA over N. Just don't get tricked. They're asking for the number of men you would expect. So the number of successful outcomes is 8. Number of total outcomes did not change. And the number of trials, we are picking 6 people. So the expected number of men would be 6 times 8 over 18. So you get 48 divided by 18, you get 2.66 or 2.7 men. So of course there's more women in the jury pool, so you'd expect more women. And this is the last example, so just to finish this off, 10 cards are drawn from a standard deck of cards without replacing it. What's the probability that at most 2 face cards will be drawn? At most. So what does that mean? So that means the probability that I get 0 face cards plus the probability that I get 1 face card. It says at most 2, so that includes 2. So this is what it wants. And again, honestly, this is a question I could have asked you on your last test. The only thing you didn't know was that this happens to be a hypergeometric distribution. So I'm not going to use the formula, I'm just going to go ahead and answer this. What's the probability that I'm dealt at most 2 face cards? So if you recall, the face cards would be the jacks, queens, and kings. There are 12 face cards out of the deck of 52 total. So what is the probability that I'm going to get exactly 0 face cards? That's going to be 12, choose 0. Well, that must mean that I got 2 other cards, or sorry, the 10 other cards must have come from the remaining 40. And then I'm going to divide that by the total number of outcomes, which is 52. How many ways can I pick 10 cards? No restrictions. 52, choose 10. Okay, now I want to know the probability that I'm going to get exactly 1 face card. Well, out of the 12 face cards, choose 1. That means out of the 40 other questions, I'm going to choose 9. then lastly, what's the probability I'm going to get exactly 2? That means I'm going to get 8. So I don't have the answers to this in front of me, but I would just go ahead and calculate that, and then that would be my probability. I will have the completed answer for that in the completed notes section when I post this. I'll also add the homework and then the review that you should maybe get started on. And again, I'll probably have an assessment ready for upload by the end of this week, and it'll probably give you a little less time to work on it. The only reason I give you the 5 days is because it stretched over the Easter weekend, but hopefully now that we got the process down, maybe 2.5 days would probably be enough to hopefully get through that. Again, just email me though, or message me if there's any problems, concerns, anything going on in your life that I should know about, and we can definitely make some arrangements to work around that. But other than that, hope everyone's doing well, and hopefully this helped.